There is a chip inside every Nvidia GPU that almost nobody talks about. Not the processor itself, not the transistors, not the AI compute units that every benchmark measures and every headline celebrates. A different chip, one that sits physically next to the GPU on the same silicon substrate, connected by hundreds of thousands of microscopic copper pillars, and without which the GPU cannot function at all. That chip is called HBM High Bandwidth Memory. Every Nvidia H100 that powered the first generation of large A1 models contains 5 stacks of HBM3. Every Nvidia B200 Blackwell chip, the system currently training the frontier models that determine where artificial intelligence goes next, contains 8 stacks of HBM3E, delivering 8 terabytes per second of memory bandwidth. Every next-generation Vera Rubin GPU that Nvidia has announced for 2026 and 2027 will require HBM4, a technology that has never before been produced at commercial scale by anyone on Earth. There are exactly 3 companies in the world that can manufacture HBM at any meaningful volume. SK Hynix in South Korea, Samsung in South Korea, Micron in the United States. 3 companies. 3 countries that are formal U.S. allies, a global market that is growing from $38 billion in 2025 to a projected $100 billion by 2028, and a supply chain that Nvidia alone consumes at a rate that accounts for roughly 90% of SK Hynix's entire HBM output. This is the choke point that nobody discusses when they talk about the China semiconductor story. Not the advanced logic chips, not the lithography machines, not the GPS, the memory. The HBM that must sit next to every AI accelerator, that cannot be substituted with any other type of memory without destroying performance, and that China currently cannot manufacture at any meaningful scale. This is the story of what China is building to fix that. Who is building it, how far along they are, and what it means for the most important memory market in the history of the semiconductor industry. If this is the kind of analysis you come to Signal Leap for, subscribe before we get into the details. The HBM story is about to become one of the most consequential technology competitions of this decade, and most coverage is missing it entirely. Before we get into what China is building, we need to spend a moment on what HBM actually is, because the physics of it explain both why it matters and why building it is so hard. A modern AI chip is, at its core, a math machine. It performs matrix multiplication, multiplying enormous arrays of numbers together at speeds measured in petaflops, trillions of floating point operations per second. The transistor count, the architecture, the precision support, all of these determine how fast the math can happen. But math is only half the problem. Before the chip can multiply those matrices, it needs the data. And getting data to the compute units fast enough to keep them busy is one of the fundamental engineering challenges of AI hardware. If you have a factory that can produce 1 million units per hour, but your supply trucks can only deliver 10,000 units per hour, the factory runs at 1% capacity regardless of how sophisticated it is. This is called the memory wall, and it is the problem HBM was invented to solve. Conventional DRAM, the memory in your laptop, your phone. Your desktop computer sits on a circuit board connected to the processor through a narrow electrical interface. The data has to travel a relatively long distance through a relatively narrow channel. The bandwidth, the amount of data that can move per second, is limited by the physics of that connection. For consumer electronics, this is fine. For AI training, where a single model update requires moving terabytes of data between memory and compute, it is a fatal bottleneck. HBM solves this by doing something that sounds simple and turns out to be one of the most difficult manufacturing challenges in the history of semiconductors. It takes the memory and puts it right next to the chip, not on a circuit board nearby. Physically next to it, on the same package, connected by hundreds of thousands of microscopic copper pillars called through-silicon vias, or TSVs. Here is what this looks like in practice. A stack of HBM3E, the current generation, consists of 12 individual DRAM dies stacked directly on top of each other, like a skyscraper of silicon. Each die is individually thinned to a fraction of its original thickness. Through silicon vias, vertical copper interconnects drilled through each die carry signals between every layer of the stack simultaneously. The entire tower sits on a base die that manages the data flow, and the whole assembly is mounted next to the GPU on a silicon interposer, a custom substrate that routes the thousands of signals between memory and processor with the kind of density that conventional circuit boards cannot approach. The interface between a single HBM stack and the GPU is 1024 bits wide. For context, a conventional DDR5 desktop memory channel is 64 bits wide. HBM is 16 times wider per stack, and Nvidia's B200 has 8 stacks. The result is 8 terabytes per second of memory bandwidth, enough to move the entire contents of a large digital library to the GPU's compute units every second. Continuously, the engineering required to build this is extraordinary. The TSVs must be drilled through silicon dies at microscopic precision. The stacking must be performed with alignment tolerances measured in single-digit micrometers across the entire die area. The thermal management must handle the fact that 12 layers of active DRAM are generating heat with nowhere obvious for it to go. And most critically, a single defective die anywhere in the 12 die stack makes the entire stack unusable. Every bad die in one stack scraps the whole assembly. This is why HBM yield rates determine the economics of the entire AI chip supply chain, and why HBM costs what it does. The 3 companies that have mastered this process, SK Hynix, Samsung, and Micron, did not arrive here quickly. SK Hynix shipped the first commercial HBM product in 2015. 10 years of iterative development, HBM1, HBM2, HBM2E, HBM3, HBM3E, HBM4, each generation requiring new stacking processes, new TSV architectures, new packaging technologies, new quality control systems tuned to the specific failure modes of ever taller stacks. SK Hynix holds 63.2% of the HBM market by revenue as of 2025, according to IDC. Nvidia accounts for roughly 90% of SK Hynix's HBM output. The relationship is so tight that SK Hynix's HBM capacity is functionally synonymous with Nvidia's production capacity. If SK Hynix cannot make enough HBM, Nvidia cannot ship enough GPUs. The market has already been sold out through 2026. Samsung holds roughly 20 to 28% of the HBM market, depending on the quarter. Micron holds the remainder, a position it has been aggressively expanding, with the company reporting HBM-related record quarters in late 2025 and describing itself as more than sold out for HBM capacity. The total HBM market in 2025 was $38 billion. Bank of America estimates it will reach $54.6 billion in 2026. The projection for 2028 is $100 billion larger than the entire DRAM market of 2024. And every dollar of that market is currently controlled by 3 companies in 2 countries that are U.S. allies. China has 0 meaningful share. And that is the problem China has been working to fix. The consortium that is leading China's HBM effort is not a startup. It is not a government agency. It is an alliance of some of China's most strategically important semiconductor companies. Assembled specifically because the HBM problem is too technically complex and too capital-intensive for any single entity to solve alone. At the center is Huawei. Not as the chip manufacturer, Huawei does not operate fabs, but as the system architect and the primary customer. Huawei's Ascend AI accelerators are the chips that are replacing Nvidia inside China's data centers. Every Ascend chip needs high bandwidth memory to function at the performance levels Chinese AI developers require. As long as that memory must come from SK Hynix, Samsung, or Micron, all operating under US export control frameworks that could change at any political moment, Huawei's AI chip program has a structural vulnerability that no amount of semiconductor engineering can eliminate. The consortium Huawei leads includes 3 other entities, each playing a specific role. CXMT ChangXin Memory Technologies is China's largest DRAM manufacturer, the company we profiled on our video on the Shanghai Stock Exchange debut that shocked Samsung and triggered Apple's Washington lobbying campaign. CXMT holds 8% of global DRAM market share as of Q1 2026, up from 3% in the same quarter of 2025. CXMT brings the DRAM manufacturing capability, the ability to produce the individual dies that get stacked into an HBM assembly. Fujian Jinhua Integrated Circuit JHICC is a DRAM manufacturer based in Fujian Province that has been on the U.S. Entity List since 2018 for alleged involvement in trade secret theft. That blacklisting cut Fujian Jinhua off from American equipment and ended its conventional commercialization path. Inside the HBM Consortium, it contributes process technology and manufacturing capacity specifically for HBM development, operating in a space where the entity list restrictions apply to U.S. exports, but not to purely domestic Chinese development. Tongfu Microelectronics is China's leading advanced packaging company. This is the entity in the consortium that makes HBM physically possible, because manufacturing the DRAM dies is only half the challenge. Stacking them, bonding them, drilling the TSVs, and integrating the assembly onto an interposer with the GPU requires packaging expertise that is distinct from DRAM manufacturing and equally difficult. Tongfu is the company that bridges those two domains, providing the advanced packaging services that turn individual DRAM dies into functioning HBM stacks. Wuhan Xinxin Semiconductor XMC is a foundry controlled by YMTC, China's leading maker of three-dimensional NAND flash memory. XMC is constructing a 12-inch wafer fabrication plant with a monthly capacity of 3,000 wafers specifically for HBM chip production. The facility was planned to commence operations in early 2025. XMC brings YMTC's expertise in three-dimensional stacking developed through years of producing layered NAND flash and applies it to the HBM problem. This is not a collection of companies stumbling toward HBM. It is a purpose-built supply chain, assembled around a capability gap that every participant understands is strategically critical. Where does the program actually stand? This is the point where the honest analysis becomes more nuanced than either the triumphant coverage or the dismissive coverage tends to acknowledge. Morgan Stanley's Channel Check research, published in mid-2025, found that CXMT had delivered HBM2E samples to customers in the first half of 2025, with mass production of HBM2E originally scheduled to begin in the first half of 2026. The same research found that CXMT had already pivoted its ambition. Rather than scaling HBM2E into full production, the company was targeting HBM3 samples for delivery to customers by the end of 2025, with full-scale mass production in 2026. Tom's Hardware confirmed in January 2026 that CXMT had supplied HBM3 samples to Chinese AI hardware developers, including, notably, Huawei. Despite the fact that Huawei's Ascend 950 series accelerators use Huawei's own proprietary HiBL memory rather than HBM. The sampling to Huawei signals that the technology has reached a level of maturity suitable for customer evaluation, even if not yet commercial production. The production plan, reported by Tech PowerUp and sourced from Korean industry tracking, is for CXMT to dedicate 60,000 wafers per month, approximately 20% of its total manufacturing capacity, to HBM3 production in 2026. Morgan Stanley's projection extends further: 100,000 wafers per month of HBM capacity by the end of 2026, potentially expanding to 400,000 wafers per month by the end of 2028. For reference, global HBM capacity at the end of 2025 is estimated at approximately 340,000 wafers per month. If CXMT achieves 400,000 wafers per month of HBM capacity by 2028, and that is a significant if China alone would represent a substantial fraction of current global production, deployed entirely for domestic AI chip supply. The packaging side is equally advanced in development terms. CXMT has adopted the mass reflow molded underfill packaging technology known as MRMUF, which is the same packaging approach that SK Hynix uses for its HBM production and a key reason for SK Hynix's yield advantage over Samsung. Adopting MRMUF is not a minor decision. It represents a studied choice to follow the most effective known packaging path rather than developing a proprietary approach that would require years of additional optimization. Here is where the honest assessment becomes essential, because the gap between what China is building and what China has delivered in HBM remains wide in ways that matter. As of April 2026, the most credible assessment of probability analysis published on Manifold Markets drawing on Semi-Analysis, TrendForce, Tech Insights, and Digitimes tracking placed the odds of CXMT achieving mass production of HBM3 by the end of 2026 at 44%. That is not a confident prediction of success. It is a coin flip weighted slightly toward potential slippage. The technical reasons for caution are specific. HBM3 production requires DRAM dies manufactured at sub-15 nanometer process nodes, the same nodes that require EUV lithography for optimal yield on die size reduction. CXMT does not have access to EUV. The company is attempting to manufacture at these nodes using DUV multi-patterning, the same technique SMIC used to approach 5 nanometer logic, applied to DRAM rather than processor dies. The physics are analogous and the engineering challenge is comparable, achievable, but with yield constraints that may limit the economics of production even when the technical capability is demonstrated. The technology lag is real. CXMT's most advanced DRAM production as of 2026 is at a 16 nanometer process equivalent to what industry analysts call 1Z nanometer class DRAM, which SK Hynix, Samsung, and Micron were manufacturing around 2021. CXMT is currently 3 to 4 years behind the global leaders on DRAM process technology. Those leaders are not standing still. SK Hynix is already in production at 12 nanometer class DRAM for its HBM4 stacks. Micron has qualified EUV-free approaches to its most advanced DRAM nodes that CXMT is studying as a benchmark for what might be achievable without EUV access. The stack height challenge adds a further constraint. The most advanced HBM3E configurations use 12 high stacks. HBM4 is targeting 16 high stacks. Each additional layer in the stack introduces another site for potential defects. tightening the already demanding yield requirements. A company that is producing its first commercial HBM3 high stacks while simultaneously developing DRAM at the process node required for those stacks is working at the intersection of two distinct hard problems simultaneously. And there is a dimension to this story that has received very little attention. The packaging challenge that Tongfu faces is, in some respects, more immediately binding than the DRAM die challenge. The TSV drilling, the micro bump bonding, the thermal compression bonding or mass reflow processes that join 12 thinned dies into a functional stack. These processes require equipment that is also subject to U.S. export control frameworks. The December 2024 export control package specifically targeted HBM manufacturing equipment alongside the HBM chips themselves. China has been holding meetings with South Korean and Japanese equipment suppliers to source alternatives, but some of the precision equipment required for HBM packaging has no readily available non-American substitute. There is one development in this story that fundamentally changes the framing, and it deserves specific attention. Huawei did not wait for CXMT's HBM program to mature before solving its own memory problem. The Ascend 950PR, the chip that ByteDance committed $5.6 billion to purchase, does not use HBM at all. It uses Huawei's proprietary HiBL 1.0, a high bandwidth memory variant designed and developed internally by Huawei's semiconductor division. HiBL 1.0 integrates 112 gigabytes of memory with 1.4 terabytes per second of bandwidth. This is below what the most advanced HBM3E delivers in peak throughput. But it is memory that Huawei controls entirely designed for its own AI accelerator architectures, manufactured without dependencies on the companies that SK Hynix, Samsung, or Micron supply. The Ascend 950 DT, confirmed to debut in August 2026 on Huawei Cloud, uses HiZQ 2.0, the next generation of Huawei's proprietary high-bandwidth memory, integrating 144 gigabytes at 4 terabytes per second with 2 terabytes per second of interconnect bandwidth. These specifications represent a substantial advancement in one generation of Huawei's proprietary memory, achieved without depending on any of the three Korean and American companies that control global HBM supply. What Huawei has done is build around the HBM dependency rather than waiting for it to be resolved. Proprietary memory, designed from scratch to integrate with Huawei's own chip architecture, removes the most visible vulnerability in China's AI hardware supply chain, not by solving the HBM problem, but by making HBM unnecessary for Huawei's specific product line. The CXMT Consortium's HBM program remains important for a different reason. HBM is not only needed by Huawei. It is needed by more threads, by Byron, by Cambricon, and by every other Chinese A-wine chip company working to replace Nvidia for Chinese customers who need hardware compatible with HBM interfaces. The ecosystem of Chinese AI chip companies that has emerged over the past 3 years is diverse enough that a single proprietary memory solution, even a good one, does not solve the supply problem for the entire domestic AI hardware stack. The CXMT program also matters strategically in a way that goes beyond current chip generations. HBM4, HBM4E, and the generations beyond them will determine the performance ceiling of AI accelerators through the end of this decade. AI training at the trillion parameter scale, at the scale of models that require 10,000 or 100,000 chips working in synchrony, requires memory bandwidth that only HBM can provide. A China that cannot manufacture HBM at the frontier is a China that cannot keep pace with AI frontier development, regardless of how good its logic chips become. The memory is not a detail. It is the binding constraint. Step back from the consortium and the yield rates and the wafer counts for a moment, because there is a larger picture that the specific details of CXMT's HBM program can obscure. The HBM supply chain is the most concentrated critical technology dependency in the global AI infrastructure build-out, more concentrated than GPU manufacturing, more concentrated than advanced logic foundry capacity, and arguably more immediately consequential than EUV lithography. SK Hynix alone accounts for 63% of global HBM revenue. Nvidia alone accounts for 90% of SK Hynix's HBM output. That is a single company supplying 90% of the output of the company that supplies 63% of the market for a component that is absolutely required for every high-performance AI chip on Earth. The supply chain is structured in a way that would concern any competent risk manager. SK Hynix's HBM fabs are in South Korea. The packaging happens at facilities in South Korea and Taiwan. The silicon interposers that integrate HBM with GPU dies are produced by TSMC in Taiwan. The GPU dies themselves are fabbed at TSMC in Taiwan. A disruption in Taiwan from any cause interrupts the AI supply chain at multiple nodes simultaneously. A disruption in South Korea interrupts it at the memory node specifically. The US government has been explicit that the purpose of HBM export controls is to prevent China's A1 chip programs from accessing this component. What has received less attention is that the control strategy implicitly assumes the HBM supply chain is secure for American and allied customers, that SK Hynix and Samsung will continue to produce and ship without disruption, and that TSMC's packaging capacity will remain accessible. These assumptions are reasonable under current geopolitical conditions. They are not guaranteed under all scenarios. China's HBM Consortium is not only solving a supply problem for Chinese A1 companies, it is, from the Chinese government's perspective, reducing a strategic vulnerability that the current export control architecture has made visible. Every restriction that identified HBM as a critical choke point also told China exactly where to invest to eliminate that choke point's leverage. This is the same dynamic we have documented across ASML's lithography monopoly, Nvidia's GPU dominance, and SMYC's manufacturing process development. The restriction identifies the dependency. The dependency becomes the investment target. The investment produces the capability, on a timeline measured in years rather than decades. For the three incumbent HBM manufacturers, the competitive implications deserve clear-eyed assessment. SK Hynix, Samsung, and Micron currently operate in a market that is sold out through 2026 and projected to grow at 40% per year through 2028. In this environment, new capacity from any source, including a Chinese consortium, does not immediately threaten their business. A market growing fast enough that the incumbents cannot satisfy demand absorbs new production without pricing pressure. The threat from Chinese HBM is not immediate. It is structural, operating on a 5-year timeline rather than a 1-year timeline. What changes the calculus is 2028, when Morgan Stanley projects CXMT could reach 400,000 wafers per month of HBM capacity if the technical and yield challenges are resolved. At that scale, Chinese domestic HBM production would represent meaningful global capacity. The question the three incumbents are already asking internally is not whether CXMT will reach that capacity, but at what technical generation, at what yield, and at what cost relative to their own next-generation products. Those questions will have answers, and the answers will arrive with semiconductor industry precision visible first in teardown reports and industry surveys, long before they appear in financial results. The HBM market in 2026 sits at the center of three converging pressures that will determine where this story goes. The first pressure is demand. The HBM market is growing at roughly 40% per year. HBM demand is growing at 80 to 100% per year. The gap between supply growth and demand growth is real, and it is not closing until 2028 at the earliest, according to the most optimistic projections. Every HBM stack produced in 2026 and 2027 is already allocated. The three incumbents are sold out. The market will reward whoever adds new capacity, regardless of geography. The second pressure is geopolitics. The US government has targeted HBM specifically in its most recent export control packages, restricting both HBM chips and HBM manufacturing equipment from flowing to China. The intent is to prevent China's AI chip programs from accessing the memory they require. The effect, consistent with the pattern seen across every other restricted technology in this story, is to create the strongest possible incentive for China to develop the capability domestically. The third pressure is time. The gap between CXMT's current technology position 3 to 4 years behind global leaders and the frontier is not narrowing automatically. It narrows only if CXMT's manufacturing yield improves faster than the global leader's technology advances. That is a race, and the outcome depends on engineering decisions, equipment access, and investment commitments that are being made right now, in 2026, with consequences that will become visible in 2028 and 2030. The 44% probability of CXMT reaching HBM3 mass production by the end of 2026 is not a comforting number for anyone counting on Chinese domestic HBM to arrive on schedule. But it is not nothing. A year ago, the HBM program was described primarily as an aspiration. Today it is described as a development program with samples in customer hands. Packaging technology selected, production equipment being procured from alternative sources, and a consortium of some of China's most capable semiconductor companies aligned behind a single objective. The chips inside every Nvidia GPU today come from South Korea and the United States. Whether they will come exclusively from South Korea and the United States in 2028 is a question whose answer is being built in Hefei, Wuhan, and Fujian right now. Subscribe to Signal Leap if you want to follow this story as the answer becomes clear. CXMT's HBM3 mass production status will become visible before the end of 2026. The Ascend 950 DT launches in August on Huawei Cloud with HiZQ 2.0 memory. The XMC packaging facility is ramping. One question for the comments, because this question genuinely divides the analysts who follow this most closely. Huawei built proprietary HiBL memory to solve its own AI chip's HBM dependency. CXMT is racing to produce standard HBM3 for the broader Chinese A1 chip ecosystem. Which path do you think wins, the proprietary architecture approach or the standards-compatible approach? And does it matter whether the rest of China's A1 industry follows Huawei's lead or waits for CXMT? Drop your answer below.